every matrix has something called a determinant, right? And with singular matrices, like I said before, there's either 0 or infinite solutions, right? So the scalar analogy would be y equals ax, where a equals 0. And it turns out that you can calculate what's known as the determinant of your matrix. And if you have a singular matrix, where you either don't have enough information, you have infinite number of solutions, or you don't have any solutions at all, that matrix will have a determinant of 0. Right? So with singular matrices, this thing called the determinant, which I haven't defined yet, but the determinant equals 0. Now, if you remember correctly, this parallel line analogy where you have infinite solutions, parallel line where you have no solutions, or the overlapping line where you have an infinite number of solutions, those were only two of like these bad situations. Remember, there was another situation where the lines were like almost parallel, like they crossed, but like, you know, near the solution there was like the slope was almost the same of the two lines. All right, y'all are looking at me funny, so I'll just go back up and remind you of the example where that came from, the illustration, right? So this one here, where the solution is there, you can calculate it, but it's what's known as ill-conditioned, right? So you have like a small calculation error will give you a very, very different solution. Right, so this is the ill-conditioned case. So how do we tell, by looking at the matrix, if it's ill-conditioned? If it's singular, we'll get a row of zeros in our Gaussian elimination, or like I said, the determinant will be 0. If it's ill-conditioned, that means the determinant will be small. So let's talk a little bit more about determinants. I'll define them, and we'll see an example of like this small situation. Okay, but before we get to that, let's look at this this almost parallel situation, this ill-conditioned situation. So example of 2 by 2 system where the slopes are almost the same. You have a matrix, let's say, 49, -5, 10, -1, times x equals to 39 and 8. This is not singular. But if you divide by the first row by 50, and you divide the last row by 10, the matrix you get to 2 sig figs is 1.0, -0.1, 1.0, -0.1, times x equals to 0.8, 0.8. I said 2 sig figs, but it was just like one decimal place, basically, right? And so this is the same set of equations because you did a legitimate row operation on the 2 rows. So it should give you the same information as the first matrix. But this one looks singular. Now, it's not really singular. If I carried more decimal places, it won't be singular, right? And so your ability to determine whether or not it's singular is dependent on what your round-off error is. Now, if you're working with MATLAB, you have like 15 or 16 decimal places. But it's possible you run into a situation where that round-off error is going to get you in trouble, right? And so how do we determine whether or not a matrix is close to singular, right? So we'll do this thing called the determinant. Okay, so let's define it, right? So the determinant here, let's say I have A equals to 6, 2, 3, and 1. The determinant of A is equal to, what you do is you take your first diagonal and multiply those two numbers together. So 6 times 1. And then you minus off the product of this other diagonal. Minus 3. Those colors don't look all that different, so I'm going to redo this. Minus 3 times 2. In this case, the determinant is 0. So it's a singular matrix. And you can tell just by inspection, right? The first row is twice the second row. So the determinant will tell you whether or not the matrix is singular. Now, this is a 2 by 2 matrix. So you could also do something similar with a 3 by 3 matrix. But let's look at a second example. And I'm running out of room here, but we'll do our best. So let's look at a second example of a different matrix. And now this matrix will be ill-conditioned, right? So let's say I have a different matrix, B, which is 4, 3, 5 times 10 to the negative 30, and 4 times 10 to the negative 30. If I take the determinant of B, that's equal to 10 to the negative 30. So it's not singular. In other words, its determinant is not 0, but it's super small, right? And so if you try to put this into MATLAB, it will give you a warning. It'll say your matrix is close to singular or badly scaled. And so it's ill-conditioned, right? So small determinants equals to ill-conditioned. Well, how small is small, right? Because small is a relative term. Is 0.1 small? Is 10 to the minus 2 small? Is 10 to the minus 3 small? It depends. It depends on how many significant figures you're willing to carry. MATLAB can handle a lot of significant figures, like I said, 15 to 16 digits. If you're doing things by hand, are you really going to carry out your calculations 15 to 16 digits? No. So if you're doing things by hand, maybe 10 to the minus 4, 10 to the minus 3 is ill-conditioned. Okay? So just something to keep in mind when you're got a system. You want to take the determinant to see if it's singular or ill-conditioned. Okay, I'm going to stop there on determinants. It gets a little bit more complicated to calculate them by hand if you have something bigger than a 2 by 2 matrix. So I'm going to leave it up to y'all to if you have to look it up on how to calculate larger determinants.